In our last video, we interpreted fundamental theorem of calculus with this new intuitive idea that was plus change equals is. This idea that a definite integral represents total change can be as boring as the last video where you're just given h prime and h and g prime and g, or it can be applied in real world situations. So let's interpret these things. So let's look at one first. If h of t is a rate of change of the height of a conical pile of sand measured in feet per hour, what does the definite integral from 0 to 5 of h of t represent? Now, this seems very familiar to me, right? I mean, we kind of talked about definite integral very at the beginning of the year as a product of units, right? The product of x and y. And if h is measured in feet per hour, I have to interpret that maybe t is measured in hours. So the product of feet per hour times hours would give me feet. But let's think about this in a slightly different way. Since this is a definite integral from 0 to 5 of h of t, I need to interpret the definite integral as the total change, right? It is the total change in the height of that conical pile of sand measured in feet on a specific interval, on the interval from 0 to 5 hours. Okay, so I might not have written that as clear as I could have, but let me say it. That definite integral represents the total change in the height of the pile. It's measured in feet, specifically on the first 5-hour interval from 0 to 5. Right? But it's this new idea that I want to just stress that this definite integral is the change in the height. Does it give me the height of the pile? No, it doesn't give me the height of the pile at 5. To figure out the height of the pile at 5, I would have to know the height at the beginning. I would have to know the height at 0. And I would have to add the height at 0 and the total change in the height from 0 to 5 to know what the height is at 5. Right? So a definite integral doesn't give me, it gives me the total change. It doesn't give me where something is. It represents total change or how tall the pile is. Keep going. Number 2, v of t is velocity, and it's a particle that's just bouncing along the x-axis, right? So it could be moving forward, could be moving backwards. It's measured in feet per second. And what does that definite integral from 3 to 10 of v of t dt represent? Now, I know what you're thinking, and I know you've probably already said it in your brain, but the first words I ought to write are the total change, right? It's a total change of what? Total change of velocity, acceleration, let's see, the antiderivative, right? What's the antiderivative of velocity? Antiderivative of velocity is, position. It's the total change of position, right? That's going to be measured in, this is feet per second, so this is going to be measured in feet on the interval 3 to 10, and that's going to be measured in seconds, right? So this is a total change of position. It's not a position. It's a change in position. How far did this particle move? What was its displacement, right? Change of position is displacement, would be another way to phrase it, right? If I think about physics. Okay, third one. B of t is the rate of growth of the number of bacteria in a dish measured in number of bacteria per hour. What does that integral 2 to 6 of b of t represent? Again, b of t is a rate of change. V of t was a rate of change. H of t was a rate of change. See where this is going? If I integrate a rate of change, I get total change on the interval. So this is going to represent the total number of bacteria that have grown in the dish on the interval from 2 to 6. It's not the number of bacteria in the dish. Right? It is the total change. It's the total number of bacteria that have grown on that 4-hour interval from 2 to 6. So how would I know how many bacteria cells are there at 6 hours? What would I need to know? I would need to know how many were there at the start of this interval. I would need to know how many were there at 2. I'm going to add the total change from 2 to 6. That's how many would be there at 6. Okay, so Couple more application type of examples. This one's a lot to read, but let's kind of break it down here. V of t is again a velocity of a particle moving along the x-axis. Now we're told a little bit more about it. The position is 5 at time equals 2. Another way to write that would be as x of 2 is equal to 5, right? The position, the x position at time 2 is equal to 5. So part A, I'm going to follow me up the screen here. Write the integral expression that represents the position of the particle at time 10. Okay, now in that other video, I have you sniff out these problems. Was plus change. Where was the particle? The particle was at x of 2, right? What's the total change between time 2 and time 10? How would I represent the total change in position between time 2 and 10? Well, that would necessitate a definite integral from 2 to 10. Now, what am I integrating? Am I integrating position? Am I integrating? I need to integrate the rate of change of position, which is velocity. That would be the position at time 10. And if you did a quick manipulation and subtracted the position at 2, x of 2, you would notice how that screams fundamental theorem of calculus. Antiderivative of velocities, the position x at 10 minus the position at 2. And all we can do is just manipulate that to get our was plus change. All right, B is going to be a bit of a curveball. All right, so write an integral expression. Really, dude? You're back in. Can y'all hear that beeping? I'm not. That's fun. We had a hummingbird the first video. We got some dude backing up here in the second video. All right. Well, let's move forward. Oh, man. It's like I planned it. Okay. So B says write an integral expression that gives the total distance traveled. How is that different? How is that different? Total distance means that all of my motion, either backing up or moving forward, all needs to be counted in the same direction. It all needs to be counted in the same direction. So how do I make it total distance? Well, let's see. I don't want my particle to be moving backwards and forwards. Right? I need my particle to be moving in the same direction. How do I get all of my particles' motion to be in the same direction? That is to say, not to the right or to the left or up or down. Oh, that's right. Right? To get my particle to be moving all in the same direction, I need it all to be the same sign. So the first thing I need to do is think about all of my velocities to be positive. Well, to do that, I need the absolute value of velocity, aka speed. Speed is always positive, always moving forward, right? When you drive in your car, when you back up, does it take mileage away from your odometer? No, it doesn't work like Ferris Bueller's Day Off. That's because you have a speedometer, right? The car calculates your speed, whether you're going forward or whether you're going backwards. It's constantly adding mileage to your car, whether you drive forward or backwards. So we're going to integrate speed on 2 to 10. So that's all of the movement of this particle is moving in one direction. So the difference between displacement and total distance is big, right? They're not the same thing. Not just a change in position, but a total distance. If I run around a track and end up at the same place that I started, then my displacement is 0. But if I think about my total distance running around a track, it'd be 400 meters, right? Those are different quantities, total distance versus displacement. Hope that makes sense in that problem. All right, last one here, and then that'll be it. P of t is the rate of growth of wabbits. Now these wascally wabbits, it's going to be measured in wabbits per year, and there's 100 rabbits in 2005. That's times 0. Okay, write an integral expression that represents the wabbit population in 2007, 2 years later. All right, so here we go. Can you smell it? Can you smell it? Kind of looks like a rabbit. P of t is a rate, right? P of t is a rate. And if you integrate a rate, you get total change. How many rabbits was there? How many rabbits? Where do we want to go? Can you think about it? Yeah, yeah. I want to say how many rabbits was there? There was 100. There was 100 wabbits, and then I want to add the total change in wabbits, and that's going to be the integral from time 0 in 2005 to time 2, which is 2 years later, and then I want to integrate the rate of change. So I want to integrate p of t dt. That is an integral expression that would tell me the total number of wabbits in the population at 2007, right? If I get rid of that 100, that integral only tells me the total change in population. So how many wabbits have been added to the population? So to know what the population is, I have to add the original amount at time 0, which is 100. Okay, hopefully this video gave you a little more application style of problems. So you could see where this idea of the fundamental theorem of calculus as total change, a definite integral as total change, can come into play. And you're going to see that a lot on the College Board tests and any question that I make up. This is an application of what we're doing. So hopefully this made a little more sense to you, and we'll talk about it this week. So, see ya.